Well, hello everybody. So this is my second video about optimization problems. And just to summarize a little bit before I get started here, the first video I made was just an introduction, and I wanted to solve one problem just so you can get a feel for how optimization problems are solved. But in our assignment, the assignment that I intend these videos to be for, there are two types of problems. And so with this video, I want to give a summary of each problem type along with a strategy for it, and then show you some examples of each. And I'll probably break this video into two parts, but we'll see. Okay. So first type of problem is where we want to find the maximum or minimum value of some function, but with limits to the variable. Okay. Sometimes this is said to be that the function is on a closed interval. So, the function is a curve, and it might go up and down, and there might be a high point on it or a low point on it. And that's what we're after when the problem says find the maximum this or find the minimum that. But if that function is on a closed interval, we're just looking at part of it. Okay, we're not looking at the entire graph along the entire axis, maybe just a little bit. So it might say, like, we want to find the max or min value of this function, but only the part of it where x is from A to B. We're just looking in this little window here, and we want to see what the max or min value is for that. Okay, that type problem might be like this one. Suppose we have an equation that models the fuel efficiency for a vehicle, and we want to find whatever the maximum and minimum fuel efficiencies are. Okay, but look at this. I've got this equation that models the fuel efficiency as a function of the speed. Okay, so the fuel efficiency of a car might depend on many things. The air pressure in the tires, some weather conditions perhaps, oxygen saturation in the air, and the speed probably. That's probably at the forefront of our mind as far as something that influences fuel efficiency. So here I've got this equation that says, well, here's how fuel efficiency depends on speed. Driving faster or slower, making the car use more or less miles per gallon. Okay, but look here. It says we're limiting the applicability of this equation to speeds between 30 and 60 miles an hour. Okay, so that would be an example of a closed interval. So let's talk about how you solve that sort of problem. First step, find the critical number. And that will be a sort of a universal step in optimization problems, but that will just be a solution to y prime is equal to 0. That's what we mean by a critical number. And say you do that, say you take your equation that you want to find the max or min value of, and you find its derivative, and you solve it for 0, and you get some number that we'll call c for right now. That's your critical number. The next step would be to make a table of the left endpoint of your interval. That's this number a, right here, this one. Your right endpoint of the interval, that's this number b, and your critical number that you find in step 1. Make a table, take those three numbers, put them into this original function, and among those results, you'll see the max and or the minimum. Okay, the biggest of these numbers will be the maximum, and the smallest of these numbers will be the minimum, and then you'll have your answer. Okay, so that's how you go about solving an optimization problem, a problem that involves finding a maximum or minimum value of some function on a closed interval. Okay, so we could take this approach to solve this fuel efficiency problem. Okay, so in fact, let's do that, and then we'll come back, we'll look at the other type of problem. Okay, so here's an example of what I was just saying. I have an equation, right? It models fuel efficiency versus speed. It tells you how those two things are influencing each other, all right? But I have a closed interval right here. My question is, what are the maximum and minimum miles per gallon within this closed interval for that function? All right, so let's go through those steps. First step was to find the critical number. And that involved finding the derivative and solving it for 0. Now, I'm going to take a little bit for granted that you're okay for the most part with the rules for finding derivatives. If that's something you're getting stuck on, then that's always something you can ask me about, okay? But let's say we mostly got that down, and we can determine without too much trouble that if this is y, if this is our function we're wanting to find the maximum or minimum of, then y prime is going to be 0.03x plus 1.43. That's the derivative of this, okay? And I take that, I set it equal to 0. I solve it, I'll get 1.43 over 0.03, and it's how you get 47.667, okay, if I round to 3 decimal places. So there's my critical number. All right. Now, it's like this may or may not be the answer to this question. All right. To really determine the answer, I need to look at my table. So here I'm making this table where I have x, my variable. I have, did I do it right? Is 30 the left endpoint for the interval in our problem? Yeah, it said that this equation is applicable for speeds. X is the speed from 30 to 60 miles an hour. So I got 30 there for the left endpoint. I got 60 for the right endpoint, and I got 47.667 for the critical number. And then that's what I said the table should include when I explain this procedure. Then I got my calculator. All right, nothing fancy here. I got my calculator and I put it into this function that gives us our miles per gallon. All right, that's this original function here from which I want to find the maximum and minimum of, okay? So these are the values I got. 30 gives you 22.3, 47.667 gives you 26.98, and 60 gives you 24.7, all right? So these are the speeds, and these are the fuel efficiencies that go with those speeds. So I would see it that, well, so 22, 26, 20. So this is the maximum. So you're going to get maximum miles per gallon or best fuel efficiency at 47.667 miles per hour, according to our numbers. And then this is our minimum. Okay, remember, I said that your maximum and minimum values, whatever they were, are going to appear over here. Okay, and I can make my judgment on an answer just like that. So let's give our final answer to the question this way. Let's say max, and I'm just going to put MPG, because now I'm going to make a direct statement that's an answer to that question, is 26.98, and that's with some rounding, but if you're working the problem on MyMathLab, follow the instructions for the rounding. Miles per gallon. All right, so that's as good as you're going to get. And the question may ask you specifics, so it might say, well, that's your best fuel efficiency, but what speed do you get that at? So I might say also at 47.667 miles per hour, okay? And that would be like a complete answer to what's the maximum miles per gallon, okay? So that's what it is, and that's how you get it. So that's my first statement as an answer to the question. And then similarly, if you want to know what the minimum is, the least fuel efficient speed, and so on, I'll get the minimum miles per gallon being 22.3 miles per gallon, at least in that range of speeds. That's the worst you can do. It's at the lowest end, 30. So minimum miles per gallon is 22.3 miles per gallon, and that's going to occur if you're driving 30 miles per hour. Okay, so that would be my statement to serve as an answer to that question. On MyMathLab, the way that it asks you to present the answer might be slightly different or want different information, but you see how we get that information from the table, okay? All right, let's try another one like this. Let's try another one where we're trying to maximize or minimize something on some closed interval. So where we have a function and it says for x between a and b, right? That's this type of problem. That's how we would handle any problem where we're maximizing or minimizing some function, whatever it is, whatever it measures, whatever it tells you or describes, where the variable is from here to there. All right, so let's do one that is totally different, okay? This is a model for the spread of a disease. And population models, disease spread models often looks like this. They often have exponential equations in them. So this was on my math lab, and I don't exactly know where it came from there, but it is a typical kind of model for this kind of thing, okay? So what we have here is a model for the spread of a disease. Y equals 8 times x times e, where e is a number that's about 2.718, raised to the power negative x over 13, okay? Where y tells me the percentage of the population that's infected, and x is the number of days since the original infection, okay? All right, now that applies from 0 days since the original infection out to 39 days. So here we see another closed interval. So just based on that, I know I'm going to take this approach of finding the critical number, making a table with that critical number in the left and right endpoints of my given closed interval, and then my max or min, whatever I'm looking for, will appear over there. Okay, so we know our strategy. So the question is, after how many days is the percentage of infected people at maximum, and what is the maximum percent of infected people? So you might gather that with the spread of a disease that it's self-limiting a little bit, that it's not like under most conditions infections could just rise and rise and rise and rise with no ceiling. You know, at some point they reach their peak and things work out with the immunity of the population and the inability to get reinfected, where you got your peak and it just goes down from there. So we've all heard a little bit about this kind of thing over the past few years, and it is a complicated subject, but this is a basic and realistic model. Okay, so what were my steps? I was going to find the critical number, and that involves setting the derivative equal to 0. Now with derivatives, I did say that I was going to not focus on the derivatives too much because I want to focus about solving the problems. But we need to find the derivative of this original function, which models the percentage of people that are infected. Okay, and to do that, I would have to use the product rule. So let me just, how about this? I won't show like all the work, every single step, but I'll summarize the rules real quick. So the rules. One, in order to find that derivative, the product rule is necessary. Okay, because I have 8x, and that's one function. And then I've got e to the negative x over 13. And that's another function. So that's like one function times another function. That's when we use the product rule. Second rule that's involved is this rule for the derivative of an exponential function. The derivative of an exponential function, let's say e to some power u, where u might be some complicated function of x all by itself, like negative x over 13 or whatever it is e to the power u, but then times the derivative of the u. So between those two things, I get my derivative like this. 8, the derivative of 8x, times e to the negative x over 13 by the product rule, plus negative 1 over 13 e to the negative x over 13. That's the derivative of e to the negative x over 13. It's e to the negative x over 13. And then what's the derivative of x over 13? It's 1 over 13, or negative 1 over 13. Then times x. So that's the product rule and this rule together. That's what you're looking at right there. From here, I did a little simplifying, okay? And here, because I wanted to solve it for 0, I factored it, okay? So I took my derivative. I see I could factor out an 8, and I could factor out an e to the negative x over 13. And if I do that, factor it out, what's left is 1 from this one and negative x over 13 from that one. Now with factoring, I could always re-multiply and see that I got what I had in the previous step. Okay, now when we're trying to solve something for 0 and we factor it, the principle works like this. If I factor something, then it is in the form of one thing times another. So I might say a times b equals 0. So a times e to the negative x over 13 times 1 minus x over 13. Multiply two things, get 0. The principle used to solve such an equation, if you've got two things multiplying and giving you 0, is that one of those things has to be 0. That's just the way it is. The only way to multiply and get 0 is multiply by 0. So one of those things has to be 0. So when I factored this, the derivative, set it equal to 0, the principle from there says, well, either this first thing is 0 or this second thing is 0. That's just what it says, because that's how you multiply to get 0. Anyway, now it turns out impossible for an exponential to be 0. You can't take a number, whatever the number is, and raise it to some power and get 0. Like right here, e, that's a number. The power is negative x over 13. Well, I don't care what that power is. You just cannot get 0. Okay? So I know that this aspect of my solution is impossible, and it doesn't yield any answer. With this other one, 1 minus x over 13, so that's pretty easy to solve for 0, and if I solve for 0, I'll get 13. So here's my critical number. That is the solution to the derivative being equal to 0. Now we had to do some work to get, that particular critical number, maybe more so than some of the others, but that is the critical number. So on our table then, notice I'm doing what is according to the procedure. I've got a left endpoint for my interval, which was 0, wasn't it? Yeah, the function applies from 0 to 39 days. Okay. Critical number was 13, and my right endpoint was 39, because 0 is 39 days. From there, I do the math. Again, with my calculator, there's nothing special about this part right here. These are what? My days into the infection, and this is the percent of people infected. Okay, I'm trying to find the maximum value of that. So I put these numbers into that function. I look at those results, and if I want the minimum, I choose the minimum. If I want the maximum, the maximum. So it says again, after how many days is the percentage of infected people a maximum? What is the maximum percent of infected people? So, well, it's after 13 days that you get a maximum number of infected people. Okay, here's my maximum. Oops. So let's make a statement of our answer from that. Okay, let's see. After 13 days, we reach a maximum number of infected people of 38.3% with some rounding. I just round conveniently, to be honest with you, when I'm working these problems for the class, but on my math lab there will be some instructions about rounding, and just follow those instructions. Okay, all right, so hopefully then with that you see how we would handle any problem that came down to maximizing or minimizing some function on a closed interval. Now let's talk about the other case. Notice, let's see, let's do this one. Here's a problem that I took a screenshot from my math lab. It's right on the assignment. And it seems a little contrived. It seems a little bit silly, but in manufacturing, when companies are trying to build something and it's got to be a certain way, and they would like to economize on the raw materials used to make it, they might not do this exact thing, but they do something like this, okay? So let me read the problem to you, and then we'll talk about how this one's different than the others, and we'll talk about how you solve it. So it says a cylindrical box, which is just a cylinder, and I just included this here as a token cylinder. Okay, that's what a cylinder is. It has a circular radius on the top and the bottom, and it has a height. You think of a cylinder as a can if you want to. Okay, so it says a cylindrical box will be tied up with ribbon as shown in the accompanying figure. Okay, like this. So it looks like there's ribbon that goes down 4 sides of this thing and across 4 sides in the top and the bottom. Okay, so I kind of imagine that there's like a bow tied here, and then like ribbon goes like that, and ribbon goes like that, and ribbon goes like that, and then it goes down and down and down, and then it goes like this too, and so on. Okay, and then it's like got to be tied down there at the bottom. So then I'm thinking that it goes like this, and or something like that. All right, I don't tie ribbons on boxes very often, so I have no clue. But I'm pretty sure that that's what they mean. So we have a cylindrical box. We're going to tie ribbon around it like that. The longest piece of ribbon that is available for this box, or like any one box that we make, is 140 centimeters long, and 20 centimeters of that is required to tie the bow. So meaning like not on the box, but just on this bow part up here. Find the radius and height of the box with the largest possible volume. So it's like, I want this box to be as big as possible. What limits that? Well, what limits that is I only have so much ribbon to tie around it. All right? So I want the biggest box, but the ribbon, that's what holds it back. That's what limits how big it can be. Now notice, this doesn't sound like the others. It doesn't say maximize this function on this interval. It's not the same kind of problem. What we do in the second type of problem, the one I'm about to work, is when it just says find the maximum or minimum value of something. Okay? Notice that there might be no equation, perhaps. You know, perhaps, like maybe there is an equation, but I think in our assignment often there won't be. And there's definitely no closed interval. All right, so if I can just get you to see that, yes, this is different. It doesn't seem like those other problems, then we'd probably be off to a good start. Now, how do you solve that type of problem? Well, you have to have an equation that you're working with, okay? So if the equation is not given, you have to find it. So must find somehow. Okay? So you have something that you want to maximize or minimize. Maybe the equation is given, maybe not. Either way, you've got to have it in the end. Here's how you proceed. You find the critical number. All right, now we've already practiced that, okay? And then if you're trying to find its minimum value, you verify that it's concave up, which was the same thing as the second derivative being greater than 0, okay? So it's like the first step, you want to find that f prime c is equal to 0. That means that c is a critical number. The second step, if you want a minimum, show that f double prime c is greater than 0. If you happen to want a maximum, show that f double prime c is less than 0. And then that's your procedure. I think the hardest part for this type of problem is just getting that original equation if it's not given to you. So I think down here in this one, that will be the hardest part. So let's think about how we'll do this, okay? Now, to me, like, this is real math. Like, we really got to think through this and read this information and try to think about, okay, what do I have? How can I use it to achieve my goal? All right, to me, that's what math really is. Just doing the same thing you saw somebody else do that involves numbers, that's not really math to me because there's not as much challenge in it. But this will really make you think. So here it goes. Here's how I would approach it. We're going to maximize the volume of the cylinder. We want that to be as big as it can be. But we got to take into account the ribbon that's involved. That's the limiting factor. So I need equations for all of that. I need equations for the amount of ribbon and for the volume, because those were the two things that were mentioned. Okay, so how would I quantify the amount of ribbon? Well, see how I kind of drew here the way the ribbon's tied onto the box? Like kind of in this cross formation like this. So first of all, in a cylinder, the distance from the middle of the circular top or bottom to any point on the outside is called the radius. So to account for all the ribbon that's there, I see 1, 2, 3, 4 links of radius on top. I see 1, 2, 3, 4 links of radius on the bottom. Okay, so see, to quantify the amount of ribbon, you got 4 R's on the top, 4 R's on the bottom, where R is the radius. R means radius, not ribbon here. Okay, now what else? I have 4 links of ribbon along the height or sides. So in a cylinder has a circular radius on either the top or the bottom, and it has a height from top to bottom. Okay, so I see 1, 2, 3, 4 H's. So there's the amount of ribbon on the top, 4 lengths of radius. On the bottom, another 4 lengths of radius. And along the sides, 4 lengths of the height. And that's going to be 120. Why 120? Well, because we have 140 centimeters of ribbon available. 20 centimeters of that's on the bow. The rest of it is in contact with the box like that. So this accounts for the amount of ribbon. Might take one more thing to simplify this. 4R and 4R, I wrote those separately so that you can see I'm taking into consideration the top and the bottom, but that would be 8R, okay, plus 4H is equal to 120. So to simplify it, all right, that's what it would be. That's the amount of ribbon. Okay, so now I've got an equation that quantifies the amount of ribbon. What about the volume? That was another thing that was mentioning. It says, what's the largest possible volume? Well, what is the volume of a cylinder? Like we need like the standard formula for that. So you'd either have to know that or you'd have to look it up. So for now, I'll just tell you, and you could solve this kind of problem with this equation in mind. But the volume of a cylinder is pi. Pi being a constant, it's about 3.14. Your calculator will have a button for pi on it, okay? Pi radius squared times height, pi r squared h. So those should be the equations that I need, all right? Now that's like the hardest part, remember, for this second type of problem, when we're just finding the maximum or minimum value, there's no closed interval that's mentioned, okay? You got to get those equations that are involved in the situation to start with. So, okay, here we are back here again. Now let me go to the next page and write down my equation that quantifies the amount of ribbon and the volume of the cylinder. So look what I have. There's that equation. 8R plus 4H is 120. That's the constraint on the size of the box. That measures the amount of ribbon. And I want to maximize the volume. The volume of that cylinder is pi times radius squared times h. Okay? The trick with this, when you have two equations, is there's this very important step of reducing it to one variable. Now, everything that we do in calculus at this level, maybe someday you'll take a calculus course where you deal with several variables at once, but in our class, the functions have one variable. Like if I say y equals x squared plus 2x like plus 1, there's just one variable over here, okay? There's one variable and it's x. But in this equation or this one, there are two. There's r for radius and h for height. So I need to reduce that to one variable. So here's the way that we would proceed. Now, I don't really expect you would just think of this out of nowhere. I mean, if you're really good at math, then you probably would. But if you're not, if you're still learning and you're not quite there yet and you don't have the experience to just come up with this out of nowhere, what we do is we take this equation here that's not the one that we're wanting to maximize, because the equation intentionally said maximize the volume. What's the biggest box that we can make with the amount of ribbon that we have to tie around it the way that it was? So, okay, I want to take the equation that's not the thing I'm maximizing or minimizing. I want to solve it for one of the variables, whichever one is the easiest to do. And then I want to plug it into the equation that I am maximizing. So it goes like this. I take my equation that measures the ribbon on the box. 8R plus 4H is 120. I think it'd be easier to solve this for H. So that's what I'll do. I'll move the 8R over. Then I'll divide both sides by 4 and I'll get this. That reduces it to H equals 30 minus 2R. Now I'll put that in for H. So it's kind of like, imagine that I got this. I know what the H is. I know H is the same thing as 30 minus 2R. So I could put up there, and it would reduce this to just having one variable, which is what I would like. So what would that be? Pi r squared times 30 minus 2r. You see, that's this part, okay? Then I'll multiply that together right here. I'll distribute the pi r squared. I'll get something a little bit easier for my derivative. I'll get 30 pi r squared minus 2 pi r to the third power. Okay, now that's the kind of thing that we can work with, and that's what I want to maximize. I want to maximize the volume. I've reduced it to one variable. I can now do things like find the derivative of it, solve it for 0 in order to find my critical number. And then since I want to find its maximum value, I can verify that it's concave down at my critical number. Now, those were the steps, okay? So we've got to find our equations that are applicable in the situation. For the thing we're trying to maximize, we have to find the critical number. And since we want a maximum, we need to prove it's concave down at the critical number, which means the second derivative is negative at the critical number. So I'm going through those steps now. So here goes. The derivative of this, v prime, 60 pi r. The derivative of 30 pi r squared, that element, bringing that exponent of 2 down makes me a 60 pi r minus, okay, 2 pi r to the third power, bringing that exponent down front makes 6 pi r squared. I solved that for 0. This is my derivative equal to 0. Okay, for me to solve that particular equation, I'll factor it. Here's how I factored it. And I get 6 pi r is equal to 0, or 10 minus r is equal to 0. 6 pi r equal to 0, that would give me an answer of 0. But that's a meaningless answer. I guess technically it's an answer, but it's like doesn't have any relevance to this actual problem. And then 10 minus r is equal to 0 gives me 10. Okay, so there's my critical number. Now what's the next step? Verify that that equation that I'm maximizing, you know, this thing right here, verify that that is concave down, okay, at my critical number. To be concave down means the second derivative of this is negative. So let's see, I have my first derivative here. My second derivative is here, 60 pi minus 12 pi r, okay. I'll put my critical number of 10 into it. I get 60 pi minus 120 pi. If I subtract those, I'll get negative 60 pi. But if you round that, you could round it, I don't know, 108, 190 or so. But it's definitely negative, okay? So that proves that there is a maximum value when r is 10. So looks like we got our answer. All right, so let's do this. Let's give a formal statement of our answer. The question was, find the radius and height of the box with the largest possible volume. Okay, so to get the volume, V for volume, to be a maximum, you need R to be 10, okay? All right, so let's write that down. R equals radius equals 10 centimeters, because those were the units of measurement, for maximum, for max volume. Okay, now that's the radius. It also said the height. So let's see, how are we going to find the height? Well, from equations. Like, do we have an equation somewhere that links those two things together? Like, do we have an equation where if you knew what the radius was supposed to be, that you could find the height? I mean, look, you can look all on my page here for such an equation. It looks like this is the one that would do it. Okay, so it's like asking me, I know that the best way, the most efficient way to build this box and make it as big as possible is for the radius to be 10 centimeters. To also know the height, well, let's see, this will get it to me. Okay, so if r is equal to 10, the height would have to come out of that because this equation governs what's happening in this situation. So I get 8 times 10, r being 10, plus 4 times h, where I don't know the h yet, and that's 120. So yeah, I can solve for the h out of this. I have enough information. So I get 80 plus 4h is 120. I move the 80 over. I get 4h. 120 minus 80 is 40. Dividing, I get h to be 10 also. Okay, so the way you want to build this thing is you want to make this cylinder. Radius is 10 centimeters. Height is also 10 centimeters. And if you do that, it will be as large as it could possibly be, given that you have this much ribbon to fit around it in that way.